Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories. One of the top stories concerns the battle of the billionaires. We recall that during the Cold War, there was this intense rivalry between the two superpowers for domination of outer space. The Soviet Union and the United States spent an enormous sum of money, up to 5% of the gross domestic product of the United States itself, reaching the moon. Now we have a new battle shaping up, a battle of billionaires. On one side, we have Elon Musk of SpaceX. Just last week, he made history by test firing the first used rocket. Think about that. Think of the used car industry. When the used car industry debuted after World War II, it literally changed the economics of owning a car. Well, think of what happens when we have used rockets on the marketplace. Not to be outdone, another billionaire, Jeff Bezos of Amazon.com, announced just last week that his goal is to create a permanent moon base and, in fact, set up a delivery system for the moon, similar to what Amazon.com has. And then, talking about outer space, we'll talk about a new breakthrough. Scientists have always wanted to take a picture of a black hole. Now it turns out that we may be very close to doing just that. A new radio telescope, created by lashing together smaller radio telescopes, has the resolving power of a radio telescope the size of the planet Earth. And it wants to take a photograph of the black hole lurking at the center of our own galaxy. The Milky Way galaxy, the black hole weighs 4 million times the mass of the sun. And then the question is, well, how can you photograph something that's invisible? And speaking about outer space, a new discovery was made just last week. It turns out an exoplanet, a planet revolving around another star in the universe. This planet is Earth-like, and it has an atmosphere. Think about this. This is incredible. An Earth-like planet that has a confirmed atmosphere. And then if it has an atmosphere, the question is, can it support life? And then we'll say something about the health front. Many doctors believe that we're facing a disease of the century in our own backyard, and it's obesity. It turns out that 1/3 of the adult population in the United States is either very much overweight or downright obese. And yet there's a paradox. It turns out that preliminary studies on obese people show that on average, well, they seem to die less. How can that be? Some people said, aha, maybe it means that all the folklore we have about obesity is wrong. Maybe obesity is good for you. Well, a new massive study came in, and the results are rather surprising. Well, let's just jump right into some of the big stories of the past week. Outer space is heating up in a way that we haven't seen since the Cold War. Just think of it. Back then, the two superpowers, the United States and the Soviet Union, were in a race to the moon, and it was a race that had no bounds. Think about it. 5% of the gross domestic product of the United States, 5% of the entire economic activity of this superpower went into NASA's budget to put our astronauts on the moon before the Soviet Union. Now there's a new battle raging, this time between billionaires, because it turns out that the cost of space travel is now reduced to the point where even billionaires can have an impact. Well, we have 2 billionaires and 3 booster rockets that are contending for this race to dominate outer space. In one corner of the ring, we have Elon Musk, founder of PayPal, not to mention Tesla Motors, not to mention SpaceX, and he pioneered the reusable rocket. Think of a rocket that takes off, Well, the first stage is the booster phase, and it's simply dumped into the ocean with a tremendous waste of money. Why not put retro rockets on the booster rocket so once it separates from the main craft, it lands by itself? It has its own retro rockets and therefore lands back on a launch pad. Well, that's exactly what Elon Musk's SpaceX accomplished, but the next step is, of course, to salvage this rocket, refurbish it, and then send it back into outer space. And that's what he did just last week. History was made. Now, think about it for a moment. Think of after World War II. Everyone wanted to have a car, but cars were still really expensive. But a new market opened up, the used car market. Today, of course, many people's first car is a used car, and it changed our lifestyle. It meant that even the average person could afford a car. Now, to put a pound of anything into orbit around the Earth costs about $10,000. That's your weight in gold. So think of your body made out of solid gold, and that's what it costs to put you just in orbit around the planet Earth. Along comes Elon Musk, who says, now, wait a minute, this is ridiculous. We throw away most of the rocket. Why not reuse it? So he put retro rockets on the booster rocket of the Falcon missile, sent it into outer space. After a few mistrials, it turns out that the booster actually could land back on the launch pad intact. And just last week, he showed that he could reuse it. Now, think of the used car industry. It changed the dynamics of American life. And all of a sudden, teenagers could roam the streets in a used car. The economics changed and our lifestyle changed. It almost became our birthright to have a used car. Well, now with a used rocket industry emerging, perhaps the cost of space travel will go down by a factor of 10. That is $1,000 to put a pound of anything into orbit. Well, just remember that Elon Musk is not the only billionaire out there. There's another one, Jeff Bezos, who happens to be the second richest man on the planet Earth after Bill Gates. That's right, he's number 2 when it comes to having amassed a tremendous amount of private wealth. With his private wealth, he bought the Washington Post. That's right. It wasn't his company which bought the Washington Post. He personally whipped out his checkbook and bought the Washington Post. And now he's whipping out his checkbook and funding the Blue Origin's missile, which will eventually, he said just last week, create the first city on the moon. In fact, he even wants a delivery system, sort of like a FedEx to the moon, so that we'll be regularly sending packages and materials to the moon. Now, this, of course, is a game changer because we're not talking about private funds. We're not talking about necessarily government funds. However, the government, of course, has its foot in the door. The United States government is backing the SLS booster rocket, a booster rocket which is designed to go around the moon perhaps as early as next year in terms of a robotic mission. So, in other words, we have not one, not two, but three possible entries to dominate outer space. The first is NASA. NASA takes the slow-go approach. It, of course, had 2 space shuttles that blew up, killing 14 astronauts, and does not want to repeat for that, and therefore is being very cautious. On the other hand, Elon Musk and Jeff Bezos, they're dynamic. They're entrepreneurs. They want to cut corners, hopefully not compromising safety in the process. So, on one hand, we have NASA with the SLS booster rocket and with the Orion space capsule, designed to orbit around the moon perhaps as early as next year, perhaps by 2020. However, we now have Elon Musk who comes in with his own rocket, the Falcon rocket. The Falcon Heavy is just like the Saturn rocket, and he wants it to go to the moon as well, and then on to Mars. So Elon Musk is setting his sights past the moon, and he wants to go all the way to Mars because he wants humanity to become a multi-planet species. He says, like many other futurists and Carl Sagan himself, it's simply too dangerous to put humanity on just one planet because think about it for a moment. A gigantic meteorite or asteroid, a planet killer, could wipe out life as we know it on the planet Earth and extinguish any hope that we could become a spacefaring species. So Elon Musk's goal is go on to Mars. Now, Jeff Bezos is getting into the game late. He has his Blue Origins rocket, which is also reusable, and he's setting his sights to the moon. Now, think about it for a moment. If we have a permanent moon base, we could take off where we left back in the 1970s, 45 years ago, when we explored the moon. We went to the moon, put the flag there, and came back and never went back. What a waste of money. Why not set a permanent base on the moon? However, the next question is, what do we get for it? Well, first of all, NASA is paid for by taxpayers' money. And as I mentioned, NASA has its sight set on Moon and on Mars, but it has a very slow time frame. In comes private enterprise with Elon Musk and Jeff Bezos with huge bank accounts capable of funding many missions just on their own, just for the sake of ego and philosophy and because they want to be the one to put the flag on Mars. And so they have a different timetable. And their timetable will, of course, have some public money, but will also be generously funded by private money as well. And that could be good for the taxpayer, because we simply don't want to spend 5% of the gross domestic product of the entire United States of America on the space program. And then the next question is, who benefits from all this space activity when we have a traffic jam around the moon and a traffic jam around Mars with not one, not two, but three independent missile systems backed by their respective billionaires? Well, take a look at the electronics wonders that we have in our living room. Think of the telecommunications, the internet, the lasers. Think of the microchip. All of that was stimulated by the space program. In fact, if you ever meet an astronaut, especially the early ones, you'll notice something strange. They're actually very short. Now, the astronauts that went to the moon were short for a reason, because we wanted to have a small space capsule to conserve money, and as a consequence, electronics had to be miniaturized as well, and a tremendous market was created for microchips. And that, in turn, helped to stimulate Moore's Law to create small chips that could be used in your PC and in your laptop. So in other words, the space program helped to jumpstart the computer revolution of today. Now, what about mining the moon? Well, this is a weak spot because, you see, the moon came out of the planet Earth. It turns out that we have moon rocks that we've taken from our astronauts. Analyzing them, we were quite surprised to find that they have more or less the same chemical composition as the planet Earth. And the reason for that is, well, the moon came out of the Earth. The latest theory is that an object about the size of Mars plowed into the Earth 4.1 billion years ago, creating the moon out of all the debris. And so, in other words, mining the moon might not be such an economical idea. Might be easier to simply mine the rocks in your own backyard. Some people say helium-3, an extremely rare substance to be used for fusion reactors, could be mined from the moon. Yes, that's true. But the problem is we don't have any operating fusion reactors yet, and the market for helium-3 is simply unknown. So let's be blunt about this. There are probably no immediate economic benefits by going to the moon and Mars. To go to the moon and Mars is a good thing because there could be secondary scientific benefits like the computer revolution, not to mention the fact that, yes, it's good to have an insurance policy rather than putting all our eggs in one planet called the planet Earth. And speaking about the planet Earth, just last week it was announced that a new exoplanet has been seen orbiting a dwarf star in the heavens, 39 light years from Earth. But get this. This exoplanet, which is a little bit bigger than the Earth, has an atmosphere. This is a game changer. Now remember that so far, scientists have identified roughly 4,000 planets orbiting other stars in outer space, most of them the size of Jupiter, with thick atmospheres. But what about an Earth-like planet with an atmosphere like ours? Our atmosphere makes possible life. And therefore, scientists really want to know, is it possible that we can have an Earth-like planet that has an atmosphere? Well, bingo. 39 light years from Earth, there's a dwarf star, and they've analyzed the mass of that planet. It is 1.6 times the mass of the Earth, and it has an atmosphere that contains water vapor, methane, and, well, who knows, maybe some oxygen as well. So this is a potential game changer. Atmospheres that are found on Earth-like planets in outer space. Then the next question is, how many Earth-like planets are there in outer space? The latest estimate that I've seen is staggering, that on average, every star in the galaxy has an Earth-like planet going around it. That's incredible. Think of all the stars you see at night. And on average, there could be an Earth-like planet for each and every one of those. This is mind-boggling. So the next time you look up into outer space, realize that somebody could be looking back. And speaking about outer space, scientists are on the verge of photographing a black hole in outer space. Well, at first you may say to yourself, how's that possible? Black holes are invisible, and they're really far away, so how can you photograph a black hole in outer space? Well, at the center of the Milky Way galaxy, our home galaxy, there is a raging black hole, dead center. It weighs 4 million times the mass of our own sun, which is puny by comparison. And you can see it tonight. That's right. Go outside, get a star map, look in the direction of Sagittarius A. In the direction of Sagittarius A, well, sad to say, you're not going to see much. There's a dust cloud that blocks the galactic nuclei. Now, by rights, if we did not have dust clouds in the Milky Way galaxy, every night a gigantic fireball. A fireball would emerge about as bright as the moon. It would be spectacular. Think about that. A galactic fireball that comes out every night at the center of the Milky Way galaxy. And dead center is a black hole weighing 4 million times the mass of the sun. Well, the next question is, how do you photograph such a thing, and what would it look like? For that matter, what is a black hole? Well, first of all, every object in the heavens has something called an escape velocity. Take the Earth, for example. To leave the planet Earth to go to the moon, you would have to travel 25,000 miles per hour. That's the escape velocity of the Earth. 25,000 miles per hour, if you can attain that, you can jump to the moon. Now, the bigger the planet, the larger the escape velocity. To escape Jupiter, for example, you would have to attain many times the escape velocity of the Earth. Well, what happens if you have a star that is so massive that gravity itself keeps light from escaping? That is, the escape velocity is the speed of light. So light is trapped. Light cannot exceed the speed of light. Well, it turns out when you do the calculation, that gives you a black hole. So what is a black hole? You've seen references to it in science fiction movies and science fiction novels, but what is the definition of a black hole? A black hole is an object whose escape velocity is the speed of light. That's it. An object whose escape velocity is the speed of light. Now, since you cannot go faster than the speed of light, according to Einstein's theory, it means that nothing can escape a black hole. So a black hole should be black on the outside, or at least gray. So how can we photograph such an object that is tens of thousands of light years away from the planet Earth? Well, astronomers use radio telescopes. Instead of looking at optical frequencies of the electromagnetic spectrum, they look at radio frequencies because stars emit radio. And these radio waves can easily be picked up on the planet Earth. Now, it turns out that the radio telescopes we have are not powerful enough to peer into a black hole. We need to lash them together. That's right. Instead of having one radio telescope, you lash together many radio telescopes, giving you an effective telescope the size of the planet Earth. Now, think about this. It's impossible for us to create a radio telescope the size of the planet Earth. However, by lashing together small radio telescopes distributed around the Earth, you can simulate a gigantic radio telescope the size of the planet Earth. And that's what they did last week. The data is now pouring in, and by analyzing all the data pouring in from multiple radio telescopes that are all synchronized, it should be possible to create a picture of a black hole. Now, what are we going to see in this picture? Well, black holes are mainly black, maybe possibly a little bit of gray, but how do you see something that's invisible? Well, the black hole itself, some people think, is nothing but a dot or maybe a ring at the very center. Surrounding this dot or this ring, there is a sphere called the event horizon. That is a point of no return. If your rocket ship falls through the event horizon, you never come out again. In other words, it's a cosmic roach motel. Everything checks in, but nothing checks out. That's called the event horizon, which surrounds the black hole. So, when we lash together all these radio telescopes, and the first image of a black hole emerges from all this data, what are you going to see? Well, you'll probably see a lot of stars, and at the very center of this carpet of stars, you see a black disk, which is the event horizon. So it's not going to be the event horizon you see in Hollywood movies, which has flames coming out and all sorts of special effects. It's not going to be anything as dramatic as that. However, the very fact that we can photograph the event horizon of a black hole is amazing. Now, also, you've probably heard that black holes eat up whole star systems. And as stars plunge into a black hole, they emit tremendous amounts of radiation and light. So you've probably seen some pictures of black holes showing the disk of radiation falling into the black hole. Now, the disk, called the accretion disk, is what you see in motion pictures. That is not the black hole. The accretion disk that makes for great graphics in science fiction movies is nothing but the hot gas swirling around the black hole that then comes right in and is eaten up as it passes through the event horizon. The black hole itself is at the center of the event horizon, and it is, unfortunately, invisible. Then the last question that even children ask is, if all these stars go falling into a black hole, where do they go? Well, the short answer is, we don't know. Einstein's theory predicts the existence of black holes, but if you take a black hole solution of Einstein's equations and go to the very center, what do you get? Nonsense. In other words, Einstein's theory breaks down at the center of a black hole. So you need a higher theory perhaps string theory, and string theory is what I do for a living. That's my day job. Now, Einstein's theory does make some predictions, rather outlandish predictions, about what happens if you go through a black hole. First of all, black holes are rotating. They rotate very rapidly. So at the very center of the event horizon, we have not a dot, but a ring of neutrons that circulate very rapidly. And if you stick your hand through the ring, you don't necessarily get crushed by the gravitational field. The field, in fact, is finite at the center of the ring, and if you follow the mathematics, if you fall through the ring, you wind up in a parallel universe. So think of Alice in Wonderland. The looking glass would be the rim, that is, the black hole would be the rim of the looking glass. If you stick your hand through the looking glass, your hand goes from the countryside of Oxford all the way into Wonderland. And if you went around and did it a second time, you would wind up on the second stage of a black hole. So in other words, a black hole has multi-stages. the more times you go through the black hole, you wind up on different parallel universes. Well, then the other question is, if there's a parallel universe on the other side of a black hole, how stable is it? And why don't we go there? Well, quite frankly, we don't know how stable they are. It may turn out that the black hole collapses when you enter it. That's the thinking of most physicists. Other physicists believe that these black holes could be unstable and perhaps disintegrate or fall apart when you try to go through. But ultimately, you need a higher theory, a quantum theory, to resolve all these questions. And that's where string theory comes in. You see, Einstein's theory breaks down at the very center of a black hole. Einstein's equations are useless. Einstein's equations simply predict that gravity is infinite at the center of a black hole. Well, that's nonsense. Therefore, you have to have a quantum theory that acts as a cutoff, that gives you a finite result. Unfortunately, string theory is not advanced enough, mathematically speaking, to resolve the question. In fact, the mathematics is so advanced that we need computers to begin to try to simulate the aspects of string theory. So at the present time, we simply don't know. So some people say you can go all the way through. Some people think you have to stabilize it. Other people say you need another substance called negative energy or exotic energy to stabilize the black hole. Well, my personal point of view is that we need a higher theory to resolve this question once and for all, and that's one of the reasons why I work on string theory. Also, on the health front, there's something called the obesity paradox. About a third of the American adult population is either grossly overweight or obese. It's a huge medical problem. But the question is, well, there were early reports showing that obese people seem to live longer. That contradicts common sense. It contradicts medical wisdom. How is it possible? Well, some people call it the obesity paradox, that young, obese people, they tend to live longer. Well, now we have a massive study that just came in last week resolving the obesity paradox. It turns out that obese people do not live longer when you look at their entire life. In other words, these earlier studies were like a snapshot looking at one point in time. Now think about it for a moment. You have to average in thin people. Sometimes people who are very thin are anemic and have problems, and they don't live very long. So in other words, if you simply take a snapshot, you get a distorted picture of the true lifespan of these individuals. That's why you need much more comprehensive studies, not simply taking a snapshot of the population. Well, I'm afraid that's it for the first part of Exploration. Once again, this is Dr. Michio Kaku. And in the second part of Exploration, we're going to bring on an expert on black holes, Professor Fulvia Melia. And they'll talk to us about what is a black hole, where do we find them in outer space, and perhaps one day, what happens if we have a close encounter with a black hole. So stay tuned. Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is the second half of Exploration. In the first half of Exploration, we talked about, the battle of billionaires. Who will dominate the race for outer space? Not one, but 2 billionaires, including NASA, are now creating 3 separate rocket systems to go to the moon and even beyond that to Mars. And, of course, one of the most intriguing objects in the universe is the black hole. And that's what we're going to talk about in the second half of Exploration. If you were to name some of the top 10 mysteries of the universe, one of them would be the creation of the universe itself. And the other one would be what lies at the center of this raging object called the black hole that we find at the center of our own backyard. in the Milky Way galaxy. If you want to see a black hole tonight, go outside, get a star map, look at Sagittarius, and in the direction of Sagittarius A, there is the galactic nuclei, and at the center of the galactic nuclei is a raging black hole. Unfortunately, you can't see much because it's obscured by dust clouds. But think about it for a moment. If it wasn't for these dust clouds, every night we would see this fantastic light show, a gigantic luminous ball of flaming stars, and at the very center of that would be a black hole. Our special guest today is Dr. Fulvio Melia. He's the author of a book called The Edge of Infinity, and we are talking about the mysterious objects in the universe photographed by the Hubble Space Telescope called black holes. Well, black holes are so massive that even light itself cannot escape. In fact, when we photograph these black holes, we actually photograph the swirling disk of matter and energy and stars that swirl around the black hole. One of these days, perhaps one of these days, we'll be able to get right up close and photograph the event horizon, a sphere surrounding the black hole. And if you were to go through the sphere, it is the point of no return. And believe it or not, in our own Milky Way galaxy, at the center of our own backyard, the Milky Way galaxy, there's a gigantic black hole. It weighs about 2 million times or so the mass of our sun. And of course, there's ample speculation about what happens if you were to fall into a black hole and wind up on the other side. The first question for you is, how did you first get interested in physics and astronomy?
Well, I actually grew up in Melbourne, and I don't know if all of your listeners have had the opportunity of visiting the Southern Hemisphere, but looking up at the sky from the Southern Hemisphere, one gets quite a different view than from the Northern Hemisphere. The Milky Way, for example, is very easily seen, and it stretches from one horizon to the next, and it fills the cosmic vault. And when I was small, I remember almost every evening just going outdoors and just looking at the stars in the Milky Way for hours and hours and hours. And I would say that that's probably what started me off. With that, of course, comes the natural curiosity of how things work and what these objects are, and one is led, I think, in most cases, to a study of physics, and that's what got me into physics and astronomy, I would say.
And Arizona is one of the world's leading centers for astronomical research, I understand. So what is it like to be in Arizona versus being in New York City, to be able to look up at the night sky and see the Milky Way, and also to be at the very forefront of telescope technology?
Well, that's the interesting comparison, of course, because even though I usually tell my friends, especially the ones overseas, even though we belong to the same country, the southwest of the United States is really very, very different from the Northeast, as I think everybody realizes. Here in Arizona, the skies are almost always clear. It's not a coincidence that many of the national and now the international telescope facilities are being built here. We get very little cloud cover during the year, so going out in the evenings, whether using a telescope or not, presents quite a glorious experience. It's a wonderful opportunity to feel the magnitude of the skies and the objects there. And of course, for research, especially for the observers and people who build instruments eventually placed on the telescopes with which these observations are made, there are very few places on the planet better than this to do studies such as this. The clarity of the skies and also the access to objects not only in the Northern Hemisphere, but those approaching what one would see from the Southern Hemisphere. Of course, Earth's rim prevents us from seeing all of the portion of the Milky Way that would be accessible from the south, but nonetheless, during a portion of the year, we can still see the center of the galaxy, for example, which is close to the southern horizon for us here in Arizona. But other than the skies here, the only other place that would present a comparable opportunity for studying these objects would be from countries such as Chile, which of course is way down south. So as far as we here in the United States are concerned, unless we want to travel to South America, this is probably the place to do this type of work.
And also, tell us a little bit about how stars die and the formation of black holes.
Right. Well, this, of course, is an ongoing investigation. We think we understand some pieces of the puzzle. Not everything is known. It's quite a long story. Black holes can actually form in several ways, and it's not clear that the supermassive objects that we see in the nuclei of galaxies form through the stellar process of life and then death. They may have formed in other ways, and we may come back to this in a few moments when we talk about the genesis of these objects early on after the Big Bang. But in terms of the smaller black holes, like the ones like Cygnus X1, for example, these are the objects that we think weigh perhaps 10 to 20 times as much as the Sun. As far as these objects are concerned, most of them are produced when a very massive star, and by very massive would mean something, an object that weighs anywhere between 30 to 50 times the mass of the Sun, burns its nuclear fuel rather quickly, it turns out, because the more massive the object is, the faster it burns the fuel, and then eventually loses that internal support that prevents it from collapsing to the middle. It's the heat generated from nuclear burning that preserves the star during the main part of its life, like the Sun is now. And at the end, when that nuclear fuel is burned to heavier elements such as carbon and eventually to iron, the heat generation stops and the material can't support itself anymore and collapses into the middle, at which point a supernova explosion ensues, and the remnant, depending on how massive the original star was, can sometimes be a black hole with a mass somewhere between a couple of solar masses and 10 to 20, as I said earlier. So the vast majority of black holes about which we know, and there are some billion of these in the galaxy, probably formed in this way. But there is another class of objects, like the one at the center of our galaxy and the center of many other galaxies, such as the Andromeda galaxy, our sister galaxy. These objects have a mass anywhere between 1 million to several billion times the mass of the Sun. And although some of them may have started as seeds from supernova explosions a long, long time ago and eventually have grown to the point where they are now, it's not clear that all of them could have formed that way. And the reason I say that, and this would lead into another part of the story, the reason I say that is that we now have very, very strong evidence that at least some of these supermassive objects were formed only 700 million years after the Big Bang, much, much earlier than the formation of galaxies and much of the structure that we see in the universe today. So it's starting to look like there was some other mechanism, some other process that led to this early collapse and this catastrophic creation of very strong gravity surrounding these objects, which probably also then acted as nucleation sites that attracted other matter towards them, and that matter, we think, in many cases, may have led to the formation of galaxies. So the odd thing now is that we may actually owe our existence to the formation of these supermassive black holes, because they may have been the seeds that created galaxies, which then, of course, created stars within them and planets and life and so on. So it's quite a long, complex story, and we don't know all the details yet, but some of the pieces of the puzzle are starting to emerge in that there definitely appear to be several classes of these, and one class having to do with the supermassive object somehow had a genesis much, much earlier than we thought before, and how they formed is not entirely clear yet.
Well, I have a question that many young people ask about black holes. First of all, black holes suck in everything. Even light itself cannot escape. In some sense, they're the ultimate roach hotel, and the Hubble Space Telescope has photographed black holes eating up whole star systems. So in other words, things check into a black hole, but nothing ever checks out. Well, then the question is, well, a black hole should be invisible. Even light itself cannot escape from a black hole. Therefore, a black hole should be invisible. And yet we have the Hubble Space Telescope taking photographs of perhaps hundreds of black holes in outer space. And so then the question is, how do you photograph something that is invisible?
Right. This is what's really generating much of the excitement these days with theoretical astrophysicists and, of course, the physics community in general. What telescopes that have been built up to this point have seen so far is not really the black hole itself, but what they see is light produced by matter falling into the black hole. Their resolution is not yet good enough for them to make an image of the black hole itself, the event horizon, which is the surface beyond which nothing can escape, including light. So if we really could see the black hole itself, what we would see is a dark shadow in front of a curtain of light. The curtain of light presumably would be produced by matter behind the black hole relative to us, and the black hole would absorb all of the light produced behind it or redirect it away from our line of sight, because gravity can bend the path of light. And so we would see a dark shadow. That's what a black hole would look like if we had a camera with such clarity, such spatial resolution that we could see detail down to that size. It does look like by the end of the decade we may have the capability of actually forming such an image. But for now, telescopes such as Hubble and Chandra have not been able to do that yet. So instead what they show us is images, or what they produce is images of matter falling into the black hole from larger distances much further away than the event horizon itself. Both have done spectacularly in this regard, though. Both Chandra, the X-ray telescope, and Hubble have each produced a very deep image of certain patches of the sky. By deep, we mean that there were patches in the sky, such as one in the constellation of Ursa Major, where there are very, very few objects within our own galaxy inside of that patch. And so it's like looking through a relatively open window to much distances much further away than objects within our galaxy. And what they were able to do by staring at these patches was to collect light from objects some 10 to 12 billion light years away. In other words, objects that were producing this light only 7 to 900 million years after the Big Bang. And what they see when they look at these patches is very bright objects, either X-ray objects or ultraviolet or infrared objects in the case of Hubble, objects that number as many as 500 within a region only the size of the full moon. So if you can imagine with your eye looking at a part of the sky that has the size of the full moon, within such a region, these telescopes have been able to produce images of as many as 500 of these objects. And these objects are so far away, they're so bright, that the only way that they could produce this much light is if they're black holes absorbing matter from their environment and converting gravitational and rest mass energy into light. So we believe that when we look at these patches, most of the objects that we see, most of the 500, must be supermassive black holes at that distance in the universe. And what's interesting is that when one extrapolates over the whole sky, these numbers correspond to total numbers of some 300 to 400 million such objects. And we know that that's not all that's there, because that's what we can count, that's what we can see. But some of these objects are probably also obscured by dusty matter falling in towards them, and so it's not clear that we're seeing everything. So the best that we can say is that there must be at least 300 million of these supermassive black holes spread throughout the cosmos. Chandra, of course, has gone on and done even much better than that. It's allowed us to look at the supermassive black hole at the center of our own galaxy with even better clarity because it's much closer than the others. It's only 25,000 light years away compared to the 12 billion light years of many of these other objects near the beginning of the universe's life. And because this object at the center of our galaxy is so close, we've been able to study it with Chandra and now other instruments as well. The European Space Agency has its own X-ray telescope called XMM Newton, which has done similarly spectacular studies of these objects. But with Chandra, we've been able to see the X-rays produced by the black hole at the center of our galaxy with enough resolution that we can actually place the source, the location of the emitting plasma, within a region no bigger than the distance between the Earth and the Sun. In addition, this object seems to explode roughly once a day, producing a flare of X-rays. The X-ray intensity during these events goes up by anywhere between 30 and 200 times what the intensity is during the quiescent state. And so for a couple of hours, the black hole at the center of our galaxy shines much, much brighter than it otherwise does. And what's intriguing now, and these are the latest results that haven't even been published in the literature, what's intriguing now is that there is very clear evidence that during these events, we can see a periodic pulse. It's like the heartbeat of this object. There's a periodic pulse that occurs roughly once every 20 minutes. The natural interpretation for this, and again, it hasn't been published yet, so we have to look at this more carefully and make sure that we've ruled out all the other possibilities. But the natural interpretation is that what we're looking at is a phenomenon associated with X-rays being produced in a region orbiting the black hole within a distance only 3 to 4 times the size of the event horizon. So although we can't see the event horizon just yet with Chandra or Hubble, nonetheless, we're seeing a phenomenon associated with a mission that's occurring only 2 to 3 times the size of the event horizon. It's similar to what would happen if you imagine putting a searchlight on a planet and being in its focal cone only when the searchlight is pointing towards you. And so you would see a pulse every time the planet goes around the sun, which would then lead to a periodicity or a period of 1 year in the case of the Earth, because that's how long it takes the Earth to go around the sun. So it's a similar phenomenon with the black hole at the galactic center. We see this pulsation roughly every 20 minutes, and so we interpret that as being part of the plasma in orbit around the black hole, and the distance that corresponds to that period is about 3 times the size of the event horizon. So these are some of the most exciting things that are happening now as we speak, and the prospects will get only better as time passes and Chandra and XMM continue to look and discover additional activity, and also with the next generation of telescopes in the pipeline now.
Now, everyone asks the question, what happens if you fall into a black hole? No one's ever done that, of course. But could you explain some of the distortions of space-time that occur if you were to fall into a black hole and someone were to observe you falling into a black hole from a distant planet?
Right. And the answer to that, of course, depends, not surprisingly, on how massive the black hole is. What one would see falling through the event horizon differs depending on how massive the black hole is compared to the mass of the object or the body falling in. It turns out that for a massive object like the one at the galactic center, which we now understand has roughly 3 million solar masses worth of material contained within it, falling through the event horizon of an object like that, a person would actually not see very much, would actually not feel very strong effects on his or her body. There would be other distortions to the light, but we'll come back to that in a moment. The point is that what happens physically to matter falling through the event horizon depends on how big the object falling in is compared to how big the event horizon is. And the size of the event horizon scales with the mass of the black hole. So, for example, if the sun were to shrink down to the size of a black hole, its event horizon would have a radius of only 3 kilometers, smaller than a city. Whereas the black hole at the galactic center has an event horizon with a radius about 1/20th the distance between the Earth and the Sun, which is much, much bigger, of course, than 3 kilometers. And it's the difference or the comparison between the size of the event horizon and the size of the object falling in that determines how much physical damage, if we can put it that way, is done to the object falling in. So because our body is so small compared to the size of the event horizon of the black hole, the galactic center, we could fall right through and not feel very much physical damage. We wouldn't get distorted or pulled or stretched or compressed. We would be able to pass through the event horizon, and then other catastrophic events would ensue, I'm sure, after that. But the process of falling in wouldn't do damage to us. On the other hand, if we were to fall through a smaller black hole, like the sun, again, if the sun were to be compressed to 3 kilometer size, then our body would get stretched at first, pulled apart, and catastrophic damage would follow. We would be disintegrated, and only the atoms and molecules would fall through. So the physical damage is different depending on the size. And a good analogy would be compare standing on the surface of the Earth, where the surface of the Earth, even though it's spherical, looks flat to us because it's so much bigger than us, and then standing on the dome of a cathedral. The dome is quasi-spherical at the top, but because the size of the sphere is much smaller compared to the Earth and much closer to our size, we feel the curvature of the dome much more. And so that's the analogy. A small black hole, because of its greater curvature relative to us, would do more damage to our body falling through than a big black hole does. Now, that's as far as physical damage is concerned. But what we see, though, would be less dependent on the size, and there would be significant distortion to the light path progressively as we get closer and closer to the event horizon. So light, because of gravitational redshift, meaning that photons have progressively less and less energy, not speed. The speed of light is always the same, but the energy of the photons decreases relative to us at infinity as they get closer and closer to the event horizon. Because of that decreasing energy, we have greater and greater difficulty seeing the light. Eventually, as the as the light reaches the event horizon, it's lost all of its energy relative to what we see, and so we wouldn't be able to even detect the light anymore, even though it would still be coming out until it passes through the event horizon, and then beyond that we wouldn't see it anymore. But as we fall in, because of this effect, we would tend to see primarily light concentrated closer and closer to the zenith angle, right above our head. So as we get closer to the event horizon, we see a progressively smaller cone of light from the rest of the universe until that point when we cross the event horizon itself, and only the light coming directly down would be visible to us. And so we would see these significant distortions because of the light bending and the gravitational redshift. And when we cross the event horizon, then of course nothing can go back out, so we can't communicate with the outside world, but what we would see is only light falling directly inwards towards us.
Now, Stephen Hawking made headlines a few months ago concerning the information problem. That is, if you take the Encyclopedia Britannica and you were to throw it into a black hole, all that information, said Stephen Hawking, would be permanently lost because it can't be retrieved. However, he took back that position a few months ago. Could you explain to us exactly what is this information problem that Stephen Hawking was addressing that made the front pages of so many newspapers?
Right. This is a very important problem, of course, because it's right on the interface between quantum mechanics and general relativity. And as you know yourself very well, Michio, there's this significant conflict between what quantum mechanics says and requires and what classical general relativity says and requires. They're almost at two opposite ends when it comes to this question of information loss and how one treats the force and so on. So in quantum mechanics, information cannot be lost.
Well, I'm afraid that's it for Exploration. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And our special guest today was an authority on black holes, Dr. Fulvia Melia. Good day.